Now see here extrinsic semiconductors. Extrinsic semiconductors are also known as doped semiconductor. Now see here, when suitable impurities are added with the intrinsic semiconductors, doped semiconductors are formed. These semiconductors can be two types, one is the N-type semiconductor and another one is the P-type semiconductor. So, when we add pentavalent impurities with the intrinsic semiconductor, N-type semiconductors are formed, and when we add the trivalent impurities with the intrinsic semiconductor, then we get the P-type semiconductor. So, now let us study about the first one is here the N-type semiconductors. How do we form N-type semiconductors? So, now see here in N-type semiconductor, first suppose you have taken like silicon atoms are here, having 4 valence electrons. So, these electrons have formed already the bonds here, the covalent bonds in this manner here. But if you add a pentavalent impurities like you take arsenic As, which has got the 5 valence electrons here, 1 here, this will form bond here, this will form here, this will is here and this will form bond here. But this electron will remain unbonded. So, this is unbonded electron. When some energy is allowed to fall on this or the temperature is increased, this unbonded electron becomes easily free because it is already tending to form covalent bond. By just adding this arsenic with the tetravalent like a silicon, so just by adding arsenic here we get large number of the unbonded electron. But when energy falls, these unbonded electron easily become free or jump to the conduction band, but at the same time the process which was taking place in intrinsic semiconductor, that will also take place. It means the bonds between the silicon will also keep on breaking, electrons will be coming free and holes will be formed. Because of that, here you will be getting Ne is much more greater than NH. So, number of electrons are much more than the number of holes here. But here if you see the energy band diagram for this, so by adding impurities you will see here the forbidden energy gap reduces. Suppose this is a conduction band here, this is a valence band which has got here the free electrons, the valence electrons, conduction band is almost empty. So, when you add the arsenic or like a pentavalent impurities, you will be getting the donor energy level comes to this point. This is called donor energy level. And for this energy gap required is approximately 0.01 electron volt. So, by giving this much of energy only, these electron can made to jump to the conduction band here, and also the electrons will be going from here to the here. So, the holes will be created. So, and these electrons easily can jump to this and conduction start. So, in the N-type semiconductor, number of electrons are much larger than the number of holes, and the relation between you will be getting here Ne into NH is equal to Ni square. That means the product of the number of electrons into number of holes is equal to square of the number of intrinsic current carriers. Now, see here this Ne and NH, these are actually electron density and hole density here. So, Ne in this case, because Ne is much more greater than NH, so Ne is known as your majority current carriers and NH is known as minority current carriers. Now, see here another type of intrinsic semiconductor, that is called P-type semiconductor. In P-type semiconductor, trivalent impurities are added with the tetravalent elements like silicon or germanium. Suppose you have taken here the silicon here, having 4 valence electrons These are the covalent bonds formed here. Now, if you look at this is if you are adding a tetravalent material, trivalent element like indium, which has got the 3 valence electrons. So, this will form bond over here, this will here, this will here. This electron is unbonded here. So, this electron of the silicon atom is unbonded, it means there is an empty space. This is called here hole, and if there is no charge, that is considered to be a positive one. So, this is empty space here, this is known as hole. So, now in this case, just by adding indium, you will be getting large number of holes here. So, NH is much more greater than Ne, and relation remain as it is previously here, Ne into NH is equal to Ni square here. Now, see energy band diagram, how does energy band change here? Here is also forbidden energy gap reduces. The reason is in this p type semiconductors, when we take like a conduction band, this is here a valence band which has got the valence electrons here, and now this acceptor label coming to this point here, this is called acceptor energy label. So, this energy gap which is here, that is 0.01 to 0.05 electron volt. So, when you give energy or when you add impurities like a trivalent impurity, you will get easily these electrons from the valence band can jump to this acceptor energy label, and also the some electrons are going to this point is also here, holes are created. So, in this case easily conduction can be started here just by making fall of small amount of energy, but again here the number of holes are much larger than the number of electrons. So, majority current carriers are holes and minority current carriers are electrons, but take care here, N type semiconductor or P type semiconductors are actually electrically neutral. They are not having negative and positive charges, because every atom if you see or every lattice you will see. So, all the charges, all the atoms are not in the ionized state. So, the each and every atom is electrically neutral. So, overall the neutrality is maintained in each lattice of the crystal here. So, N type semiconductor overall has got the 0 charge net charge, that is a neutral, and similarly here the P type semiconductor is also electrically neutral. So, these are about the N type and P type semiconductors.